Gravity is one of the most important forces in our lives, and it affects everything from how athletes perform, to how rockets launch, to why objects fall the way they do. In this lesson, we're breaking down exactly how gravitational force works on Earth's surface, why it changes depending on where you are, and what that really means for motion, weight, and free fall. Let's start with a simple idea. Earth creates a gravitational field around it, a region where any mass feels a pull toward Earth's center. This force field isn't just around us. It extends far above the surface, influencing orbiting satellites, the International Space Station, and astronauts. We measure gravity using gravitational field strength, which is the amount of force acting per kilogram of mass. On Earth's surface, this value is about 9.8 newtons per kilogram downward. That means every kilogram of mass experiences 9.8 newtons of force pulling it toward Earth. This is the same number you've seen as the acceleration due to gravity, 9.8 meters per second squared. The units n kilogram and m per second squared are equivalent in this context. To calculate the force of gravity on an object, we use the familiar equation Fg equals mg. Multiply mass by 9.8 nanokilograms, and you get the object's weight, the actual force of gravity acting on it. This brings us to a key idea. Mass and weight are not the same thing. Mass is the amount of matter in an object and never changes regardless of where you go. Weight is a force, and it depends on the gravitational field strength at that location. Change g, and the weight changes, even though the mass stays the same. Gravity is not identical everywhere on Earth. Because Earth is not a perfect sphere, it bulges slightly at the equator. The distance to Earth's center changes depending on latitude. Gravity is slightly weaker at the equator and slightly stronger at the poles. Altitude matters too. Higher elevation means you are farther from the center of Earth, so gravity is slightly smaller. On mountaintops, g decreases. Below sea level, like at the Dead Sea, g increases slightly. Now let's connect this to real life. During the Mexico City Olympics in 1968, athletes were competing at 2,300 meters above sea level. The reduced gravitational pull made sprinting, long jump, and throwing events a bit easier. Records were broken. But the thin air also meant less oxygen, making long-distance events much harder. This shows how small changes in gravity and air density can influence performance. Next, let's clear up the idea of weightlessness. Astronauts orbiting Earth are not actually weightless. The gravitational force acting on them is still about 90% of what we experience on Earth's surface. They appear weightless because they're in constant free fall toward Earth. Their forward speed keeps them from hitting the surface, so they fall around the planet instead of down to it. Everything inside the spacecraft falls together at the same rate, creating the floating effect. This is better described as constant free fall, not the absence of gravity. Newton originally explained this idea with his famous cannonball thought experiment. Imagine firing a cannonball horizontally from a mountaintop. At low speeds, it falls to the ground quickly. At higher speeds, it lands farther. But if the ball is launched fast enough, the ground curves away beneath it at the same rate that the ball falls. It never hits the surface. It enters orbit. This same principle applies to satellites, the space station, and astronauts. So to summarize, gravity on Earth is not uniform. Weight depends on gravitational field strength, mass stays constant, and orbital motion is simply a special type of free fall. Understanding these ideas helps us explain athletic performance, engineering challenges, satellite motion, and even what astronauts feel in space. If you found this helpful, don't forget to like the video and subscribe to support the channel. Your support helps us create more clear and easy to understand educational content just like this.